One of the biggest puzzles we're facing right now is energy. How do we get power that's both clean and always on? It's always felt like you have to pick one, right? Clean energy or reliable energy. But what if you didn't have to choose? It's something people in the energy world call the energy trilemma. So, on one side, you've got your clean stuff, wind, solar, and they're great. Zero carbon, fantastic. But you know the deal. They're not always on, the sun sets, the wind dies down. Then on the other side, you've got the workhorses, the things that have given us 24/7 power for a century, coal and natural gas. Super reliable, but they've got that big carbon footprint. It's always been this trade-off, this big compromise.
So, what if there was something that could actually bridge that gap? A clean, carbon zero power source that's designed to fill in when the renewables just can't.
And that's exactly where this new idea comes into play. We're talking about small modular reactors, or SMRs for short. Now, it's really important to get this. These are not just mini versions of the giant nuclear plants you're used to seeing. No, this is a totally different way of thinking about nuclear power, from the design to how they're built, and most importantly, how they approach safety. The name itself actually tells you a lot. Small, modular, reactor. So let's break that down, starting with the first word, small. And trust me, in the nuclear world, what small means can change, well, pretty much everything. Okay, so small means less power output, right? We're talking under 300 megawatts, whereas a traditional plant is pushing over 700, sometimes way more. That obviously means they take up less space. But the really key thing is that they have a smaller core. This leads to a smaller radiological source term. I know that sounds super technical, but all it means is there's just less radioactive stuff inside to begin with. And that one simple fact, it has huge implications for safety. All right, next up, modular. This is a real game changer in how these things are built. Think about old nuclear plants. They were these massive, one-of-a-kind construction projects that took like a decade to build on site. The whole idea with modular is to flip that script. You build the parts, the modules, in a factory, standardized, like an assembly line. Then you just ship them by truck or train and snap them together on site. It's a shift from the old economy of scale, building bigger is cheaper, to the economy of mass production, making lots of the same thing is cheaper. But honestly, the biggest deal, the thing that really separates SMRs from everything that came before, is a completely new philosophy on safety. It's all about moving away from relying on complicated add-on systems and instead relying on the fundamental laws of physics to keep things safe. So let's look at a traditional reactor for a sec. One of the biggest worries has always been those huge pipes that connect all the critical parts. I mean, they're massive. And the fear is, what if one of them breaks? That could cause what's called a large break loss of coolant accident. Basically, the water that's supposed to be cooling the core could drain out really, really fast. SMRs come at this problem with a solution that's, well, it's just so elegant. It's called an integral design. The idea is simple. Instead of having all those big pipes running everywhere, you just put all the important stuff, the core, the steam generators, the whole shebang, inside one single solid container, the reactor pressure vessel. And this is a perfect example of that new safety philosophy we talked about. Because all the big pipes are just gone. The risk of a large pipe break is eliminated. Not managed, not mitigated with extra pumps, it's eliminated by the design itself. It's an inherent feature. You're not adding complex systems to solve a problem, you're designing the problem out of existence from the start. This brings us to the second huge safety innovation, the shift from active to passive safety. Okay, so active safety is what you'd think. It needs stuff to work. It needs electricity, it needs pumps, it needs operators to flip switches. Passive safety, on the other hand, is designed to work all by itself. It uses the basic laws of physics, things like gravity and natural heat circulation, to keep the reactor cool. No power needed, no people needed, it just works. The goal here is what they call walk-away safe, and that's pretty literal. In some of these designs, the passive systems can keep the core cool for a week or even indefinitely, with absolutely no outside power and nobody touching anything. The reactor basically cools itself down using nothing but the natural flow of air and water. Okay, I know what you're probably thinking. These are some pretty big claims, right? Walk away safe, inherently safe. And in the world of nuclear power, you can't just make claims like that. You need an incredible amount of proof. So, how do they know these new passive systems will work the way they're supposed to? And that is a totally fair question. I mean, you can't just build one and cross your fingers. The answer is
They prove it through this incredibly intense, multi-step process of validation.
First, it all starts on the computer. We're talking thousands and thousands of hours of super advanced modeling. Engineers use these complex software codes to simulate literally everything you can imagine, from a totally normal Tuesday afternoon to the wildest, most unlikely accident scenarios. They're predicting second by second exactly how the reactor would respond.
Next, every single one of those computer runs gets put under a microscope. It has to measure up against incredibly strict regulatory standards. I mean, this table you're seeing, that's just a tiny, tiny piece of the rulebook. The designers have to go line by line and prove that their new design doesn't just meet, but exceeds the safety rules that have been built up over decades.
And then comes the most important part, the real world. See, nobody just trusts a computer model on its own. You have to prove it works. So they build these massive test facilities that can actually simulate these accident scenarios for real. And this chart right here says it all. The bar on the left, that's what the computer predicted the pressure would be. The bar on the right, that's what they actually measured in the real-life test. Look at that. They are almost exactly the same. This is how you build confidence. This is how you know the physics will do what you expect it to do.
Now, it's really important to remember that SMR isn't just one thing. It's not a single technology. This is a whole world of innovation that's happening globally, with tons of different companies and countries working on their own unique designs.
So yeah, a lot of them use regular old water as a coolant, just like the big reactors do today, but a lot of them are really out there. I mean, you've got designs that use helium gas or liquid sodium, or even molten salt, where the fuel is literally dissolved into the salt itself. It's pretty wild. And each of these different coolants opens up a whole new set of possibilities. And that flexibility isn't just about design, it's about what these reactors can do. We're not just talking about making electricity for the power grid, though they can certainly do that. Because they produce such high-temperature heat, you could use them to create clean hydrogen fuel, to power industrial plants that make steel, to desalinate ocean water, or even to provide heat for an entire city. Okay, so we've looked at the tech, the safety, the different uses. What's the bottom line here? What's the promise of these SMRs? And, just as important, what are the big hurdles they still have to clear? Well, the promise is definitely compelling. You're talking about a fundamentally safer, much more flexible kind of nuclear power. One that's built in a factory and can perfectly complement wind and solar. But the hurdles are very real, too. Regulators need to figure out how to license these brand new designs. The whole cheaper because it's factory-built idea, that has to be proven in the real world, at scale. And just building the supply chains to manufacture all these parts, that's a huge job. So SMRs offer this really fascinating vision for our energy future, one where we don't have to choose between clean and reliable. The tech is moving fast, the safety designs are being validated, and the very first ones are actually being built now. Which, of course, leaves us with the ultimate question. Will this new generation of reactors live up to all this promise? Will they actually reshape the way we power our world? The answer to that question, well, it could define our energy landscape for the next 100 years.